Okay, so we're going to dive into a world that starts with almost nothing. Just a blank grid, a single tiny creature, and that's it, two simple rules. But from that simplicity, something absolutely incredible is born.
So let's just start with the big mystery right up front. How on earth can a system with only two of the most basic instructions you can imagine create this? I mean, just look at it. This is the path our little creature carves out after about 11,000 steps. It looks complex, right? It's chaotic, but there's also something structured in there. How is this even possible? Well, let's break it down.
So our little artist, the creator of that amazing pattern, is called Langton's ant, and it lives in the simplest world imaginable, just an infinite grid of black and white squares. That's its entire universe.
The first rule is super straightforward. If the ant lands on a white square, it does three little things. 1, it turns 90 degrees to its right, a clockwise turn. 2, it flips the color of the square it's on to black. And 3, it takes one step forward. That's it. That's the whole rule.
So what's rule number 2? This is the beautiful part. The rule for a black square is almost exactly the same. The ant still flips the color, it still moves forward one square. The only difference, and this is the single knob you can turn in this whole system, is that on a black square, it turns 90 degrees to the left, counterclockwise. That's it. That is the entire genetic code for the universe we're about to see.
Now, the journey this ant takes is really like a story in 3 acts. It's this amazing narrative that goes from simple and predictable through this long, messy middle to something completely unexpected.
Act 1 is simplicity. When you watch the first couple hundred steps, the ant's behavior is, pretty tame. It makes these small, often symmetrical little patterns. It feels contained. You can almost wrap your head around it. But this is just the opening act.
And then things change. Big time. Those predictable little patterns just completely fall apart.
Welcome to Act 2, Chaos. For the next several thousand steps, the ant's path just looks like a total mess. It builds this big, sprawling, irregular blob of black and white squares. There's no pattern you can see, no logic. It honestly just looks like random noise.
And it stays in this chaotic phase for what feels like forever. But then, right around the 10,000 step mark, something amazing happens. The chaos suddenly begins to organize itself.
And right out of the middle of all that randomness, this incredible, totally unforeseen order starts to appear.
And here it is, Act 3, the highway. The ant locks into this repeating cycle of exactly 104 steps. And this cycle builds a perfectly straight diagonal path that just goes on, forever. It will never break this pattern again. This is it, a stable, complex structure that emerged from a simple system after a long period of chaos.
So, okay, this is a really cool visual, but why does it matter? Is it just a neat little computer trick? No, because this simple N is actually telling us something really profound about how complexity and even computation itself can work.
What we've just seen is a perfect textbook example of something called emergent behavior. This is a huge idea in science. It's where you get these complex high-level patterns from a bunch of simple low-level interactions. Think about it. No single rule told the ant, build a highway. The highway just emerged from those two little rules playing out over and over.
Now, here is the really mind-blowing part. Langton's ant isn't just making a pretty pattern, it's computing. It's a type of system called a Turing machine, which is the basic theoretical model for like every computer you've ever used. In fact, a study back in 2000 actually proved you could set up the starting grid in a way to make the ant calculate any logical problem you want. This little two-rule creature is a universal computer in disguise.
And if you think that's wild, get this. Our ant is just one citizen in a huge universe of creatures just like it. By just making tiny little tweaks to the rules, you can create entirely new worlds of behavior. For instance, our ant's rule could be described as RL, turn right on the first color, left on the second. Simple enough. But check out what happens if we use more colors and change the rule to left, left, right, right. Suddenly, the chaos is gone, and it's replaced by this beautiful, perfectly symmetrical growing crystal. A tiny change in the rules, a totally different universe.
And we can take this even further. Researchers have generalized this whole idea into something they call termites, which is a fun mashup of Turing machine and termite. These are basically ants that can use way more colors and can even have their own internal moods or states that change their behavior. And that leads to an explosion of complexity. For example, you can get termites that don't build highways at all. Instead, they build these incredible, intricate spiral patterns that grow outwards forever. Just look at that. Others can build even crazier stuff. Check this one out. It painstakingly fills in a solid triangle, and then the entire triangle starts moving across the grid as a single object, all from a simple set of local rules. And you know, a lot of these termites never find that perfect, clean order like our first ant. They just create new, richer, and more beautiful kinds of chaos. It's like every new rule set creates its own unique piece of digital art. And that leaves us with one last big thought. That highway, it seems inevitable, right? But believe it or not, nobody has ever been able to mathematically prove that the ant will always build a highway from any starting grid. There's still a tiny mystery at its heart. And that really makes you wonder, doesn't it? What other incredibly simple rules, just like the turn of an ant, might be quietly working behind the scenes, creating all the profound and beautiful complexity we see all around us in our own universe?